Part 3. Common ion effect on acid ionization. Furthermore, another type of problem that might be asked is to find the concentration of anion that an acid produces when dissolved in a solution of a certain pH. This problem might be asked because not all acids are dissolved in solutions of pure water. Some are dissolved, as can be seen here, in solutions that already have another acid dissolved. So they're dissolved, this HA is dissolved in a solution that already has a high concentration of H+. So basically what this does is that, let's say an acid dissolves in regular water. This acid releases a bunch of its H+, they combine with H2O to form the hydronium right here. This reaction right here goes really forward, like it goes full speed ahead like normal. But let's say the acid, this acid right here, is dissolved in water with a lower pH and more H+ that are already dissolved. So all of these H+, yeah? And these H+ by themselves already combine with H2O to form all of these hydroniums, H3O+. So there's a problem. If this water is already like crowded up with these H+, the acid has a more difficult time releasing H+, because this water is already crowded with H+. It's kind of difficult to shove more H+ into the crowd. And basically this forces this reaction, to go more backwards, to shift more to the left. So this reaction shifts more to the left because these H+ can't get released that much from this acid in a solution that is already filled with these H+ already present. It's kind of difficult to release more H+ into a solution that already has a lot of H+ and a low pH. And that is what is known as the common ion effect. We know that the acid releases an H+, and this solution already has H+ prior to when the acid was added. It already had a lot of H+. Since H+ released and H+ already present are the same ions, these are common ions. And if there is already a common ion in the solution when that the acid releases, let's say this ion in solution is already the same as the ion that the acid releases, then when the acid actually dissociates in the solution, it already has a more difficult time giving away its ions, dissociating, because there are already a lot of the same ions already present in the solution that already crowd up the solution, not allowing so many of these new ions of the same type to get added. And that is the common ion effect, and it reduces the dissociation of this acid in solution. And now we're going to see how we can solve problems to find, let's say, how much acid dissolves in a solution that already has, let's say, a lot of these common ions, a lot of these H+ present prior to the acid dissociating. Now let's say we have the following problem. We have 1.5 molar of acetic acid, HC2H3O2, with a Ka, because acetic acid has a Ka of 1.8 times 10 to the negative fifth, and this acid is dissolved in a solution with a pH of 2. So this is an acidic solution. So we need to find the concentration of the C2H3O2- ion released by the acetic acid when it is dissolved. So in order to solve this problem, we first have to understand what is happening. In this case, the reaction for the dissociation of acetic acid is HC2H3O2 combining with H2O, and that will yield H3O+ and C2H3O2-, because the H from the acetic acid combines with the water and creates the H3O+. And the equilibrium equation for this reaction is H3O+ times C2H3O2- on the top, and the final concentration of the acid HC2H3O2 on the bottom. This is at equilibrium. But in this case, since we're dissolving this acid in a solution with a pH of 2, that means it already has a lot of H plus ions in it, and therefore a lot of H3O plus. That means that this concentration of H3O plus, there's already a decent concentration of H3O plus in the solution. And that means that this reaction shifts to the left because there is already a crowd of these H3O pluses present, and it's difficult for this acid to dissociate more. Hence, if this acid dissociates in a solution with a pH of 2, which already has a lot of H3O+, not so much of these are also going to get produced, the C2H3O2-, since there is already so much H3O+ that the acid's going to have a difficult time coming apart in the solution. So how do we find the concentration of the C2H3O2- ion released by this acid when it's dissolved in a solution of a pH of 2? Well, we use our Ka equilibrium equation again, like we did for our other acid problems. We know that the initial concentration of the C2H3O2 is 1.5 molar, as mentioned here. 1.5 molar acetic acid dissolves in the solution. And we know our Ka, which is 1.8 times 10 to the negative fifth, and it's mentioned right here. Furthermore, we know that if the solution has a pH of 2, that means there are already a lot of these H3O+ ions present initially. So we need to find that concentration of H3O+ measured initially to find out how much additional H3O+ this acid adds when it dissociates. And to find the concentration of H3O+ that are present at a pH of 2 initially, we know that the pH equals 2. We know that our pH equation, negative log of the concentration of H3O+ equals 2, the pH. So in order to solve this logarithm, we take 10 to the negative second power, because this logarithm has a base of 10. It's like a hidden little thing right here, but it's actually a base of 10. And we do 10 to the negative second power, and we get 0.01 molar of H3O+ initially present. So we write 0.01 molar of this H3O+ already present. And this is at the initial point, like there's none of this C2H3O2- yet present, because these are just the initial concentrations. We do not know how much of this will be present in the end, so we just write an X for it. So we obviously know that this Ka equation is not for the initial concentrations. It's not for when the acid was 1.5 molar, it's when it actually dissociates to make more of this and more of this. So to find these final concentrations, we just do what we did previously. 1.5 minus X, because a certain concentration of this acid dissolved, and it produced an X amount of this C2H3O2-. So we don't know how much, but we know that it produced the same amount as the concentration of the acid that dissociated, because it's in a 1-to-1 ratio. So minus X, and here it's plus X. And we know that in addition to that, it produced an equal concentration of this H3O+. So if an X amount of here dissociated, an X amount here got produced. So an extra X to this 0.01 got produced on top. Because here H3O+ and C2H3O2- are in a 1-to-1 ratio, so these X's are in a 1-to-1 ratio. So an X of C2H3O2- gets produced, and an additional X of H3O+ gets produced, which gets added to the already present concentration of 0.01 molar H3O+. However, if you are going to solve this equation, good luck to you, because that is, you can solve it, but it might take a while, and you might not have that time on the exam. So we will use our small number approximation. In this case, we know that the initial concentration of the acid is definitely more than 100 times greater than this Ka of 1.8 times 10 to the negative fifth. It's definitely more than 100 times greater. That means we can take this X on the bottom right here out. We can cross it out right here. Cross it out. because this X is negligible, because the initial concentration of the acid is so much greater than 1.8 times 10 to the negative fifth that so little of this acid actually dissociates that this minus X, we don't need it. The bottom value essentially stays the same. And we can do actually the small number approximation on the top. Since this initial concentration of H3O+, the 0.01, is definitely more than 100 times greater than 1.8 times 10 to the negative fifth, we can also cross out this plus X, because the amount of H3O+ added here is very small. It's in fact negligible, because the Ka of the acid is so much smaller than the initial concentration of H3O+, that whatever X is added here essentially does not change this initial concentration. It's just so small. So we can also cross out that X. And in the end, we get 1.8 times 10 to the negative fifth equals 0.01 times X over the 1.5. So let's go on to the next step. Now that we know that 1.8 times 10 to the negative fifth equals 0.01 X over 1.5, we can multiply 1.5 by 1.8 times 10 to the negative fifth, and we will get 1.8 times 10 to the negative fifth times 1.5 equals the 0.01 X on top. And then 1.8 times 10 to the negative 5 times 1.5 is 2.7 times 10 to the negative 5, and this equals the 0.01 X. Divide the 2.7 times 10 to the negative 5 by 0.01, and we get 0.0027 molar of this X. And this X, remember, was the concentration of C2H3O2 minus that was produced by the acid. So our answer is 0.0027 molar of C2H3O2 minus that was produced by the acid when it was dissolved in a solution with a pH of 2. So that is how you solve a common ion problem for an acid.